Thank you everyone for attending. Georgios, I'm a machine learning engineer at Facebook, and today I'm going to present part of the work I did during my PhD at EPFL. And this work finished in October. So let's start. The talk is about private distributed learning in a Byzantine world. And let's go through an example to understand the concept and what these terms are. And this example is, I'm confident, familiar to many of you. So we have these keyboard typing assistants that are typically for our mobile phones, and given a sequence of words, they give recommendations for the next word the user is going to type. So this is the state on my device and the state of a friend's device. And as you can see, given the same sequence of words, we have different set of recommendations. In other words, the service is personalized. And typically there are sequential models used like LSTMs for this task. And these are tailored to the user's data. But we're not going to go into more details about how these recommendations are generated, but focus on the training procedure for the machine learning models involved in a high level. So how is this done? Typically, we have the devices that generate data, and this data is, in this example, the sentences that we type. And this data is sent to some service, some cloud, which trains or updates a machine learning model. And this machine learning model is then pushed to the device for providing the latest and greatest recommendations. And what is the problem with that? The problem with that is that there can be privacy violations. And that doesn't necessarily mean that there have to be adversarial attacks or security violations, but even simple bugs can be enough for that. And there are many regulations of Europe and in the US that try to prevent that from happening. So in this talk, I will describe a promising setup for addressing this problem. So what is this problem again? We have very sensitive data. I wouldn't feel comfortable sending my typed sentences to some cloud. I'm sure you feel the same. So we have very sensitive data sent to the cloud for machine learning purposes. What can we do? We can push the data. We can keep the data in the devices. We can keep them where it's generated, and instead of sending the data, send some models or model updates that the server or the service provider will collect and will use to create the next greatest and latest global model that incorporates the knowledge from all the devices in a privacy-preserving manner. And therefore, we can all have good utility for our service and keep our data private. Why is this idea relevant now? And this idea, we call it distributed learning because we want to make the computation done on multiple machines. You might hear about it as termed as federated learning. It's more or less the same thing. We just want to keep it a bit general. Why is this relevant now? This is relevant now because we have devices that are basically small computers. Our mobile phones are like small computers. They have very good computing capabilities. They can train neural networks, and they can exchange information with each other very fast and with almost negligible cost. Now, for this presentation, we are going to focus on two challenges that arise in this setup and describe the contributions for addressing these challenges in a nutshell. The idea is for everyone to understand what these challenges are, and the slides for the contributions may contain some more technical terms, and they have some asterisk. So don't worry if some things sound a bit not familiar. So let's go on. Let's start with the challenge of fast data. To again understand this challenge, let's go through an example. We have Alice and Bob. Bob is shown here, that use the same news recommendation application. And Bob wakes up, takes his commute to go to work, and there is some accident in the metro, and Bob delays. There is a huge delay, and then Bob interacts heavily with an article talking about this accident. For example, he likes, he shares it, and he interacts with it. And then Bob goes on with his day and eventually goes to sleep and put his device into charging and idle mode. Now we have Alice, which is waking up later than Bob and takes a similar way to go to work. But Alice tends to read the news from her app before she does the commute. And what would be really beneficial for Alice here is to be able to get this recommendation for the accident before Alice goes to work. So the data, which data? The interactions of Bob, so the clicks, the shares, and so on, that make this article relevant to Alice is very temporal and can quickly become stale. We want our recommender to be able to incorporate this fast. If Alice, so what is the state of things as in federated learning, which is, again, we want to keep the setup general. So federated learning is basically a form of distributed learning, as we described it before, with the constraint that the devices have to be idle and on charging state with a Wi-Fi connection when they make these computations. So when they have these local computations. And this can only be done during the night. So in this case, there is a high chance that Alice will miss the valuable information. A promising alternative that we propose is an online alternative where we want to push the computation as close to the data generation as possible. So while Bob is reading this article, we want to launch a background task and make a small update to the model that is then sent to the server and therefore have a good chance of giving good recommendations to Alice. Now, of course, this doesn't come for free. We have to sacrifice some of the battery of Bob because at this point, Bob is moving. He hasn't got his phone charging. And that's why we need Flitz. So Flitz is, so this slide has an asterisk. It may have some terms which may be not familiar to everyone. So we have Flitz. Flitz is a system for online learning and employs two components. The first is iProf and the second is ADA-HGD. The idea is that we have this trade-off. We have to sacrifice some of Bob's energy and impose some latency as well. So we want to control this. We don't want to give a workload which will take an hour to compute and drain all the battery for Bob. So for that, we use iProf, which does performance prediction by profiling the device of Bob. And for the second basically constraint, we cannot let Bob's device wait for someone else to communicate with the server. We want Bob's device to send the update to the server as soon as it's ready. So we talk about asynchronous communication that we ensure with ADA-HGD through staleness awareness and update dampening. Now let's move on to the second challenge, which is the challenge of Byzantine failures. And talk about two of the contributions here. So I will describe what the term Byzantine is, but let's revisit our setup beforehand. So we have the devices that generate this sensitive data we described before. This can be the keyboard typed sentences. And instead of sending this data to the cloud, the devices send model updates. The server aggregates some of these updates or all of these updates to create the latest and greatest new global model that is then sent to each device for this process to continue. So we focus on gradient descent, a very popular optimization algorithm. And for this algorithm, the learning can be visualized in a high level as follows. You have a loss function that you want to minimize. So we are at this stage here at this point, and we want to reach this point here. So we have some devices that push the model to the correct direction, right? These are the arrows shown here by the black dashed arrows. So these are the opposite of the gradients of these guys. And what can happen is that we might have this guy which is trying to pull the model in a different direction. And this guy, we call it Byzantine guy. And we borrow the term from the distributed computing field, where a Byzantine failure is a term to encapsulate an arbitrary failure, so the worst kind of failure. What are some sorts of some cases of Byzantine failures? This can be software bugs. This can be corrupted data, or even worse, security violations, adversarial attacks. And what can be the effects of a Byzantine failure in terms of learning? For that, we have TensorFlow, that we deployed with 19 workers, and one of them has a very mild form of Byzantine failure, namely, this worker just has corrupted data. And as you can see here, this has catastrophic effect for the learning. On the blue curve, we can see for an image classification task, the learning. The higher the accuracy, the better the utility. And the x-axis is the time. And on the orange curve, we can see what happens even if you have one Byzantine worker. So the learning fails. And this happens if you have a Byzantine failure. So in a relatively good scenario, Byzantine failure can make your learning diverge, and basically your model have null utility. In a more dangerous case, the Byzantine failure can manipulate the state of the model and manipulate the predictions, and that could lead to dangerous results. So what do we propose? First, we propose Aggregator. Aggregator is a system built on top of TensorFlow that does synchronous gradient descent. By synchronous, I mean that the server blocks till all the devices respond with their updates that they compute locally. And how does Aggregator tolerate Byzantine failures? Aggregator does response filtering, so tries to filter out the adversary by comparing the pairwise distances between the gradients. We have theoretical guarantees for the convergence of this algorithm, given some bounds on the number of Byzantine failures as a portion of all the workers. We have compatibility with TensorFlow, and the other thing we have is, now that we know that we tolerate the Byzantine failures at a higher level, so at the algorithm level, we can say we use an unreliable communication channel based on UDP that can have packet losses, and these packet losses are essentially a form of Byzantine failure that we tolerate, as I mentioned, in the algorithm level, and this enables us to get a performance boost. Now, for the challenge of Byzantine failures, what can happen if we want asynchronous updates? As we described in the challenge of fast data, for some applications, we have data with high temporality. So we need to process the updates fast without blocking. And in this case, we have a more complicated scenario. What can happen? We have the server creating, at this point in time, a model version 10, which is pushed back to the devices. The devices go through a new round, they collect more data, and these guys here, we are at this stage for the model, they have a new update. This is essentially proposing a new model version 11. What can happen is that we have two things here. We can have at the same point an adversary proposing a model version 11, but computed in a different way, trying to pull the model away. And we can also have at this point a node that is correct, is honest, but is computing a model which is left behind. So this is a struggler that is computing an update based on model version 4, and that's why it's proposing model version 5. So we have this green arrow, this additional green arrow here. And the question is, how do we differentiate between the red and the green arrow? And the answer is, we don't need to differentiate. We have Cardam, we propose Cardam. This is an algorithm for asynchronous gradient descent that is doing, again, response filtering, but as opposed to Aggregator, now Cardam only sees a single update. So it cannot compare updates with each other. Therefore, it has to rely on cost function statistics. Again, we provide guarantees for the convergence of this algorithm, and this algorithm has also stateless awareness, similar to ADA-HD that we described on Flitz. And with that, I would like to conclude this presentation. So we described a very promising setup for privacy-preserving machine learning that tries to keep the data where it's generated. And there are two challenges that are not addressed in this setup. First is the challenge of fast data, where we have very temporal data that needs to be taken into consideration fast. And second, we can have some machines which are unreliable, or we can have Byzantine failures. You can find information about the papers and contact information for myself in this website. Thank you very much for attending, and happy to take any questions.